All right, let's talk about one of the most powerful tools out there for making sense of the world, hypothesis testing. Seriously, this is how we go from a bunch of data to an actual decision. It's how we challenge a claim with cold, hard evidence. You see it everywhere, from medicine to marketing. It's really the engine that drives discovery. So let's dive right in.
So let's start with a problem. Imagine you're up against a huge claim. And I'm not talking about a few things. I mean millions. Millions of products, millions of people, you name it. How on earth do you test something like that? I mean, really, how could you ever check every single one? It's just not possible, right?
Okay, let's bring this down to earth. Picture this. A company says every single muesli bar they make weighs exactly 250 grams. So are you going to sit there and weigh every bar that rolls off their production line? No way. It's completely impossible. So what's the move? How do you actually test that claim?
Well, this exact kind of problem is what statistics is all about. It's built for this stuff. Since we know we can't test everything, we do the next best thing. We grab a small, random sample, maybe 100 muesli bars, and we use that little sample to make a really confident conclusion about all of them.
And there's a proper structured way to do this. It's not just a wild guess. It's a tried and true method for taking what we learn from a tiny sample and turning it into a super reliable decision about the whole big picture.
And that amazing tool is called hypothesis testing. The best way to think of it is like a recipe, or maybe a set of rules for a fair investigation. It's what takes us from just having a question to having a conclusion that's actually backed up by data.
So when you boil it all down, a hypothesis test is really just a structured process. It's a way to use what we know about a small group, that's our sample, to check if an idea about the entire group holds up.
Okay, so if we're going to run this investigation the right way, we got to know the rules of the game. There are basically three core concepts that make this whole thing tick. So let's break them down, one by one.
First up, we have something called the null hypothesis. You'll often see it written as H0. Just think of this as the boring default position. It's the assumption that, well, nothing interesting is going on. For our muesli bars, the null hypothesis would just be, yep, the average weight of the bars is 250 grams. Our job, then, is to collect some data and see if it's strong enough to make us doubt that starting assumption.
All right, next up is the p-value. Honestly, the best way to think about the p-value is as a surprise meter. That's it. It asks a really simple question. If we assume the null hypothesis is true, so if the bars really do average 250 grams, what are the chances we'd get a sample that looks like the one we just got? So a really low p-value means our result is super surprising. It's really unlikely to happen if that initial claim was actually true.
But that, of course, leads to the next big question, right? We've got this surprise meter, but how surprised do we need to be? Where's the cutoff point? How low does that p-value have to get before we can say, you know what, this is just too weird. I don't buy that null hypothesis anymore.
And that brings us to our third and final key concept, the significance level. You'll also hear it called alpha. This is our line in the sand. It's the threshold for surprise that we decide on before we even look at the data. That's super important. The standard is usually 5% or 0.05. And what we're saying is, look, if the result we get had less than a 5% chance of happening just by random luck, that's surprising enough for us. That's enough evidence to reject our starting assumption. So, at the end of the day, the decision is dead simple. You just compare two numbers. If your p-value is less than or equal to your alpha, boom, your result is officially surprising enough. You get to reject the null hypothesis. But if that p-value is bigger than alpha, you don't. You can't reject it. There's even a little rhyme to help you remember. If the p is low, the null must go. Okay, so that's all the theory. Let's make it real. Let's see how these three key pieces, the null hypothesis, the p-value, and our significance level, all come together in an actual study. This one's about income levels in Austria. Okay, so first things first, we've got to state our null hypothesis. And remember, that's the nothing interesting is happening assumption. So in this case, our H0 is simply there is no difference in the average monthly income between men and women in Austria.
Then, and this is key, before they even crunched a single number, the researchers set their decision line. They set their significance level, alpha, at 0.05. That's that classic 5% threshold.
All right, now it's time for the data. They went out and surveyed 1,200 people, ran the numbers, and the test spit out a p-value of 0.04. So what does that mean? It means there's only a 4% chance they would have seen an income gap this big in their sample if, in the real world, there was actually no gap at all.
And now for the moment of truth, the decision.
It's super simple. We just compare our two numbers. We've got our p-value of 0.04, and we compare that to our alpha, which was 0.05. And, yep, 0.04 is definitely less than 0.05. So, since the p-value is low, lower than our line in the sand, we reject the null hypothesis. The null must go. Our conclusion? The data shows a statistically significant difference in income between men and women in Austria.
But hold on, we need to talk about a really crucial warning here. Even though we reach that conclusion, it doesn't mean we're 100% certain. We can't be. Remember, we're only looking at a sample, not the entire country. And because of that, there's always a small chance our test got it wrong.
And there are actually two ways we could be wrong. The first is called a type 1 error, which is basically a false alarm. That's when we reject the null hypothesis, but we shouldn't have. We found something in our sample that isn't really there in the population. The other is a type 2 error, and that's a missed discovery. That's where there is a real difference out there, but our test just wasn't sensitive enough to pick it up. It's always a balancing act between these two.
Okay, but there is one more critical piece of the puzzle here, and honestly, if you take one thing away from this, let it be this. Just because the result is statistically significant does not automatically mean it's practically significant. It doesn't mean it actually matters in the real world.
I mean, think about it. If you have a massive sample, like millions of people, even a super tiny, totally meaningless difference, let's say an average income gap of €1 a month, that could end up being statistically significant. But does a €1 difference actually matter to anyone? No, of course not. So you always have to ask yourself, is this difference big enough to be relevant? Context is absolutely everything.
And just so you know, what we've gone over here is the general playbook. Statisticians have this huge toolkit filled with all sorts of specific tests. There's a different tool for every job, whether you're comparing 2 groups, or 3 or more groups, or maybe you're looking for a relationship between different categories.
So at the end of the day, hypothesis testing isn't some kind of magic. It's just a disciplined, structured way to challenge ideas with actual evidence. It gives us a framework to stop saying, I think, and start saying, I have evidence that suggests. It's all about methodically measuring surprise. We can make better, smarter decisions. So I'll just leave you with this question to chew on. What's a common belief or a claim you hear all the time that you would want to put to the test? Thanks for tuning in.